I want to do an introduction. Ken Griggs, he's been here before. He has a bachelor's in theoretical physics and aerospace mechanical engineering from Princeton University, master's in theoretical physics from the University of Maryland, mentored by Jim Gates in superstring theory and Sasha Migdal in simplicial quantum gravity. He's also a former software engineer for the DoD via GE Aerospace, Martin Marietta, and Lockheed Martin, former patent examiner for the USPTO, former CEO of Imagine Studios, co-inventor with Jeremy Rys of Huther Brothers, and the inventor of Phoenix theory for 31 plus exciting years. Now, so Ken is joined today. He has a co-presenter, Drew O'Meara. Drew is a Cornell grad in computer science, former U.S. Navy 688I nuclear submarine officer, former CTO of Sound Spectrum and now Plan Systems, veteran software developer, building software platforms for over 25 years, and an inventor with licensed software to Apple, as well as a specialist in 3D technology, information visualization, and distributed systems. So Ken, I would like to introduce you. Let me hand things over to you now, sir.
Thanks, Tim. I really, really appreciate you guys inviting me back again. This time we've come with my friend Drew, who is for Phoenix, our grand wizard software engineer. And what we really wanted to do today was to take a step back a little bit with Phoenix and introduce it in a way that it's usable for everybody. I think the last time that we actually talked about Phoenix, it was a little bit over the edge. So Drew had a fantastic idea to make it actually something that people can use and work with. I can't see Drew, but Drew, if you're there, can you just
hello. Hi everyone, Drew here.
Okay. And so we're going to start the presentation and share the screen. Yeah. Okay. Yay. Okay. So again, sorry to kind of waste your time with a little bit of that stupidity there, but so we're Drew and I are going to be co-hosting this presentation, and we want to take you from really a workable beginning. Last time we kind of got really deep into how Phoenix works without maybe helping you to understand how to really assemble the pieces. So we've already gone through an introduction to me and Drew a little bit, but we certainly wanted you to be able to read these slides at some future point. So I'm very happy to have Drew on the team because he's such a wonderful computer scientist, and he's given Phoenix all new insights into how to actually build up a workable algorithm for anybody in the future to be able to do particle physics using the algorithm. So Phoenix technically is a theory of everything. And that's a really big statement, you know, everyone knows, but what we want to do, at least in this presentation, is to help you to understand how do we get to that kind of a statement by showing at least how we get the standard model a little bit out of Phoenix. So what we're able to explain in Phoenix very simply are things like lepton flavor universality, which is a very big deal right now at our CERN collider. Also, in the future, we'll talk about dark matter. We'll explain why there's an asymmetry between matter and antimatter, which is still a very hot topic in physics. We'll demonstrate why general theory of relativity is really an emergent theory and not simply a ground, you know, sort of at the same level of quantum mechanics. We'll then engage later on, not today, but later on to demonstrate how do you get quantum gravity out of all of this stuff. We'll be able to simply talk about why the proton is actually what one might call a fundamental particle, as opposed to a particle that actually breaks apart. And we'll also be able to explain today the number of quark generations. And you guys might be aware that there are 3 quark generations, but we'll be able to assemble that from what we talk about today. So the Standard Model presents physics as a set of continuous particle fields that interact on a flat space-time background. So Phoenix presents physics basically using graph theory. And what's important about it is that there are very simple construction rules about how do you assemble particles and what constitutes a particle, and also what constitutes how particles interact and how they transform. So Phoenix very basically uses vertices and edges in order to combine these vertices that we'll talk about into particles. So in this assemblage technique, one often finds that there are many particle types that are very much not interacting. And what we demonstrate is that these particle types actually constitute what we want to call dark matter. And so the complexities of how particles actually interact and how particles are assembled and how particles degenerate is very simply explained in this framework. Okay. There we go. So these are some examples of actual legitimate graphs. These graphs actually constitute what we want to call particles. But again, we'll get into that. Let me go back one. My apologies. Sorry about that. Okay. So again, these are actual graphs. These are legitimate. These are particles, but we're going to explain how do you actually see particles from this stuff. So here we are. What the heck is a particle? So in Phoenix, particles are simply constructions of attaching various vertex types. Right here, we're showing on the right-hand side that there are 4 basic types of vertices. The first one we call a gamma vertex. We'll find out later on that it really describes a chunk of energy. The second one we call a down vertex, which obviously we're naming because it really is the down quark. The third one is an up vertex, the up quark, and the final one is an electron. Now, what you'll certainly notice is that each one of these vertices has 3 connections associated with it. Those 3 connections allow this vertex to either be connected to itself. When you see a loop, that's a vertex connected to itself, or it can be connected to another vertex. But in Phoenix, every vertex has to be connected in 3 different ways, and these are the 3 ways. Now, when one is trying to understand what the heck is a particle versus what is not a particle in Phoenix, again, we just showed you 3 different building blocks, vertex building blocks. But as you notice in the middle there, these are 3 particles. These particles are obviously constructed from building blocks. But if one is looking at what's not a particle, we have that on the right-hand side. And what we're trying to show is that a particle must always have vertices that are all connected in this way that you see in the middle. That is, that every vertex is really directly connected to other vertices in 3 different ways. And that constitutes a real measurable particle. Now, one asks, well, okay, so what are these building blocks if they're not real particles? And we actually just said to you in the prior slide that, like with the down quark and the up quark, that's why they constitute quarks. Quarks are not particles that you can actually measure in and of themselves, if you know much about particle theory. And the question has always been, well, why is that? And what we're demonstrating here in the middle, for example, is that they always have to be connected. That's what constitutes an actual graph in Phoenix. So it does help to resolve one of the critical questions of quark theory, which is why you can never actually observe an up quark or a down quark or a strange quark or a charm quark all by themselves. These graphs constitute that reason. So here we have actually examples of fundamental particles that actually are these constructions. So we've got the electron, which is a beautiful particle simply because it does not require being connected to other vertices. And in that way, we begin to understand why the electron shows itself in our measurements as a point particle. However, these other systems do not exhibit that point particle consequence. So the muon and the proton and the neutron, etc. Now, when we get back to the muon, we'll demonstrate eventually why it seems to also have this point particle measurement property, even though it looks like there are 3 vertices. Okay. Now, when we were just talking about these up quark and down quark and pieces of energy, or these gamma vertices, what we didn't talk about is that how a vertex actually connects to itself. It can take on 2 forms. When a vertex connects to itself in a positive way, we call that a loop. However, a vertex can also connect to itself in a negative way. Now, this kind of a construction allows Phoenix to accommodate a new concept, which is antimatter. But it is very consistent with graph theory that you allow for these 2 different types of connections. So in the end, we go from what we thought were simply 4 vertices to now actually having 10 vertices. And these are the building blocks of Phoenix. Now, there was a long time ago when I was working with Jeremy that he actually gave a great word to these building blocks, and he called them the atmos, which I'll let Jeremy explain if he wants to a little bit. But this atmos concept allows us to think about the building blocks in terms of how we see quarks and how we see matter. That there are really, normally there are 3 types of matter. There's energy, there's matter, and there's antimatter. However, in this conceptualization, we have a 4th type, and we call it queer matter because I happen to be gay. But it's also because this type of matter is almost a hybrid between matter, antimatter, and energy. And this hybrid type of matter, this queer matter, actually has some very important properties in particle physics. And in fact, one of the most important properties is that it constitutes the weak nuclear force, that trilogy in the bottom. And so the weak nuclear force comes about because we have this pi plus and this pi minus, which are actually, in this case, acting like W plus and W minus vector bosons. And then this queer quark, which is a very interesting particle because it doesn't actually have a measurable electromagnetic effect. In other words, when you actually see this particle, it's really difficult to measure it. And one of the ways that we can see it is that it appears when it binds to itself as a Z0 particle, which happens to be the 3rd vector boson that's associated with the weak nuclear force. But the beauty about this, these 10 vertices is that they nicely partition themselves into the things that we call matter and antimatter and energy. So here, what we want to show is a simple assemblage of these various vertex types that give rise to the particles that we can measure and call particles. So in the first case, we find that an up quark can be assembled into with an anti-up quark to form what we would normally call a neutral pi meson. In the second case, we're going to take a d quark and assemble to it an up quark and another up quark, and thus create a proton. And in the final case, we're going to take a chunk of energy and assemble onto it an up quark, and then 2 down quarks. And that is what constitutes a neutron. Now, how one actually works mathematically with these structures is using matrices. So every one of these wonderful graphs actually has a corresponding matrix. The matrix approach is really the essence of how you, again, work with Phoenix. We will demonstrate much later on, and hopefully in future presentations, how you get to use these matrices to see all of the defining properties of these particles, but also how they interact with each other. So in the first case, this very simple one vertex particle is what we call the electron. It's very simple. It only has one element in its matrix. However, in the second case, we have a photon, which has 2 vertices to it. And as we'll notice on its matrix representation, the off-diagonal elements are actually composed of 3s. We'll get to that in a moment. But the on-diagonal elements are actually composed of 0s. And that's simply because there's nothing on each one of the vertices is not self-connected. Now, in the third case, we have an electron that's being added to or interacting with a positron. And as you can see with the matrix form, the electron takes on the +3, the positron takes on the -3. And then in the final case, we have a proton that we were talking about before that has 2 up quarks and 1 down quark. Now, how one builds a matrix from these quarks is not actually that difficult. The first thing you want to do is to identify with a label, namely number 1, number 2, number 3, what the vertices are. And so this particular mapping here tells you how to take what's happening to a single vertex and give it a value inside of the matrix. So for example, if we're dealing with edges, then if 2 vertices are not connected by an edge, then in the matrix representation, there's a 0, an off-diagonal 0. If there is an edge between 2 vertices, then the off-diagonal element has a 1 if there's a single edge connecting it. If there are 2 edges connecting the vertices, then there's a 2. If there are 3 connecting the vertices, then there's a 3. And because every vertex exactly has 3 things on it, there can at most be 3 edges. So if we go to how a vertex connects to itself, we find the same thing, which is a vertex cannot have something on it. And in on the diagonal part of the matrix, it will have a 0. It can have 1 thing on it, in particular, let's say a loop, then you put a +1 in that space. If it is a arrow, we call it, you put a minus in that space. If there are 2 loops, you put a 2 in that space. If there are 2 arrows, you put a -2. And if you have an arrow and a loop, you add their values together. So a 1 and a -1 gives you 0, and you put a 0 in that space. So again, that's just matrix construction. So let's show you what can happen when you're actually using this matrix representation. In this particular case, we can explain pair production, which is very simply, how does a photon actually spontaneously become an electron and a positron? The way that's represented here is that the actual matrix for the photon has 2 zeros on the diagonal, 3s on the off diagonal. But strangely enough, there's a transformation, what we call a similarity transformation, that will take that matrix representation and turn it into an electron and a positron, which is what we've been talking about all along in terms of the types of particle graphs that can spin off here. So we have a photon becoming an electron and positron, and we can also show that you can have an electron and a positron that can be combined to show the same photon. And again, all of this can be performed with the matrices. And so in the end, how Phoenix represents this back and forth transformation between a photonic system and an electron and positron is just with a nice double arrow at the bottom. So we have an electron and a positron that can equally become a photon, and a photon system that can become an electron and a positron. So it's very nicely, quickly, neatly represented. Something a little bit more detailed would be what the heck happens when we have a neutron. So what we're representing here is a free neutron. In other words, there's nothing really happening to it. If you look on the left of that neutron, we have its matrix representation. And what we can demonstrate in Phoenix is that through this, you can have two possible transformations. In the first case, we have a proton and pi meson that spins off. And in the second case, we have a very, very, very rare phenomenon where you can actually spit out an electron and a very strange particle that comes along with it for the ride. We'll be talking about that in a much further lecture if you guys are interested. But this is what happens to a free neutron in Phoenix. Now we can make that a little bit more complicated if the neutron, it might be in association with the photon anywhere in the vicinity. And in that case, we have a secondary thing that happens to a neutron when it decays. That secondary effect can actually be seen in the 1, 2, 3, 4, fifth line here, where we see that the neutron in that photonic interaction can actually spin off an electron, an anti-electron neutrino, and a proton. And so what we're demonstrating here is that how the neutron interacts as it's just sitting around in space can actually spin off what we really do know as the second type of a particle reaction dealing with the neutron decay. That is that it turns into a proton, an anti-electron, neutrino, and an electron. But there's a lot of other stuff that can happen too. So the standard model, which is really the essence of what we're trying to demonstrate Phoenix can actually create. So this way of constructing particles using these various vertex types does simplify the standard model. In other words, we can produce the standard model with a much smaller building block system. In other words, the standard model as it exists today has about 61 particles to it, 61 fundamental objects. And that's a hefty set to deal with. However, Phoenix, as we've just seen, actually only has 10 actual building blocks to give you all of the particles that we can observe, and even dark matter that we haven't observed, but we know exists because of its gravity. So in this way, Phoenix names every possible particle in the way that the periodic table of elements names every possible element and the properties before the samples were ever obtained. In other words, this is basically a periodic table of fundamental particles. So you already know the standard model periodic table, and this is it. And what we want to represent here is how do you designate the down, the strange, the bottom, which are these -1/3 quarks, and the up and the charm and the top, which are the +2/3 quarks, and the the electron neutrino, the muon neutrino, the tau neutrino, as well as the electron, the muon, and the tau, and this wonderful inner circle of the photon, the gluons, the vector weak particles of the Z naught and the W plus and the W minus, and most of all, the Higgs particle. So we've overlaid here the systems or the graphs that actually constitute these particles. And what you'll notice, for example, when we go through the quarks, is that what allows a quark, in our case, our graphs, to actually constitute a quark are the number of vertices that are associated with it and the type of loops that are actually on the vertex. So for the down quark, there's only one loop. For the up quark, there are two loops. And what makes these higher generation quarks is very simply how those original single vertex systems like the down and the up connected to other vertices. And when we look at the neutrinos, we find that those actually constitute entirely measurable real particles. But what allows you to have higher order neutrinos is that they are connected to more and more what we call gamma vertices. And the same thing with the muons and the tau and the electron. And as we notice in the middle, the same thing with these force particles. That what makes the force particles either different from each other or bigger versions of each other are the number of gammas, these vertices that connect in three ways that are attached, or how the loops and the arrows are actually differently attached to each other. So, and then the final representation, the Higgs, is this wonderful photonic-like structure that actually has a very interesting quirk to it that we'll get to later on when we talk about gravity. But the idea is that that particle is what allows these particles to actually have something we call mass. And again, that's just them purely on their own. So we can represent the standard model very nicely, very easily, and with all of the right features. So that's what brings all of this together. So Phoenix shifts how we look at fundamental particles. It constitutes, this idea that particles are really building blocks, which we are all very familiar with. However, the building blocks are actually a lot easier than anyone has ever represented before. And that ease of these particles being represented allows us to do some very simple graphical representations and matrix representations that we will basically show in later presentations. You'll be able to calculate all of the characteristics of these particles. But the idea is that these particles actually show not only the same notion that we understand with the standard model, but they also show how these particles that are built from them give rise to the same transformations of particles in nature. Let's see. An important artifact here as well, and we've been saying it from the beginning, is that we can demonstrate why dark matter is such an overwhelming feature of the universe. One of the simplest ways of saying it is that in our construction of particles using these vertex types, when you create asymmetric graphs, those asymmetric graphs tend to be not very reactive. And because of that, they constitute dark matter. But we will go into showing how we can actually reconstruct why only 5% of the universe constitutes visible matter and why 25% of the universe constitutes dark matter. And then inevitably, we'll talk about what dark energy is all about on top of all of this. And that's really what's next in terms of presenting to you guys what Phoenix is. I think that, so we've covered dark matter, but one of the funny things that we haven't talked about, it hasn't been enough time, is that there's also something called dark photons. And what a dark photon represents is what happens when dark matter meets dark antimatter. So you would expect that since everything's dark, whatever photonic system it actually produces is equally dark, which seems to be a little bit of a controversy, but we're not the first ones to actually present something called dark photons. There have been various physicists, and we'll present that and hopefully in the next presentation, who have come up with a whole, what you might call, periodic table of dark photons and dark matter systems. But what's also equally important to us is that we have an ability to map out antimatter and then something else called negative energy. Now, of course, what's important in this conference is not just what constitutes matter, but one of the critical questions coming from, for example, the Alcubierre warp drive is the idea of how does one make negative energy? And so we will talk about that hopefully in the future if you guys invite us back. because I do understand how critical it is to the understanding of at least the Alcubierre warp drive. And then something that's also fundamentally important is this idea of neutrino oscillations. And it's one of the sort of big modes of understanding when it comes to particle physics, because it's still, I mean, we can measure it, but we're not exactly sure where in the standard model it's really emanating from. It's still a very big question, just like antimatter on some level. And so we always offer the idea that we need help. There's still a lot of work to be done, and also monetary help. The idea is that a lot of this stuff is done on a volunteer level. And so our doors are open for anybody who wants to volunteer time, and we can sort of walk through and teach these fundamental ideas and raise you to where we are currently with Phoenix. There's still quite a need for help in moving our project forward. And we'll be forming a new website. We already have the website, but we're still building it. And it's called phoenixtheory.tech. So hopefully by fall, we will have a construction out there so that everyone can come in, dig in, find out some stuff, learn a little, and hopefully want to contribute a lot. So without further ado, we're up for questions, and hopefully we have some substantial answers. So let's just open it up.
Wonderful. Well, before we do that, so Ken, thank you again. Let me stop your share here real quick. And I want to put this on gallery view. Everyone, please put your hands together for Mr. Kenneth Griggs. And we also have Drew here with us. Thank you, sir. Thank you very much.